here, so we're just gonna keep this express train running. Next we have Jeff Pittman, Senior Staff Engineering Manager at Google Translate. Wave your hands, everyone, if you've ever used Google Translate in simultaneous speech. Okay, we have, it's picking up. All right, I think in some way or form, most of us have. Take it away, Jeff.
All right, thanks, Talia. Hopefully everyone can hear me okay.
Yes.
Let me get the presentation up. Does that look good?
Yes.
All right, thanks for the introduction. As Talia introduced, today I'll be talking about simultaneous speech translation in Google Translate. Just to put things into context, when I joined the Translate team 5.5 years ago, the Syrian civil war was raging and the number of refugees reached over 4 million people. These refugees immigrated to many different countries, and during this time, we heard many stories about how Google Translate was used in refugee camps or used to help people get settled in their host countries. One story in particular has been really an inspiration to me. A boy named Hamoudi fled with his family to Canada. He and his sister used Translate's speech translation to gain more confidence as they learned English. Stories like this give me strong motivation to solve these hard problems that will benefit people just like Hamoudi. In today's talk, I will be covering 5 key areas. First, I'll give a brief overview of how our speech translation feature has evolved over the years. Second, I'll talk about the challenge of long-form audio input, especially in difficult production settings. Third, I'll talk about streaming translations and some of the trade-offs we had to make. Fourth, I'll talk about streaming text-to-speech and some of its challenges. And finally, in putting it all together, we'll discuss how we evaluated the feature, and then I'll show what it looks like in the product. Okay, let's take a look at the work we've done prior to simultaneous speech translation. In 2011, we launched an initial form of conversational turn-taking. It was a very basic implementation and one that many developers start out with. Take audio, send it to speech recognition, take that transcription and send it to translation, and then use text-to-speech to emit that text. These are the 3 components of automatic speech translation, whether it's in the form of turn-taking or simultaneous speech translation. How you tie these components together is another equally important area to invest in. We can call this model orchestration. In the first implementation, I do 3 components in the app. For each component, we set up a TCP connection, send out requests, and receive separate responses. For the most part, it worked okay. In a sense, it was a good demonstration of what we could do at the time. But when orchestration was on the client, we could see latency ranges that were on the order of 3 to 6 seconds. Which brings to mind what Larry Page used to commonly say: latency is a feature, in particular low latency. So around 6 years ago, we worked on a project to merge these components behind a single streaming TCP interface. The results were incredible. After pushing the orchestration up to the server, we started seeing 1 second at 90 percentile to 3 second at 95 percentile latencies. A big improvement over the previous implementation, and the improvement had led to a doubling of usage. But we weren't it. Now that model orchestration was completely on the server side, we started to look more closely at the components we're talking to each other. What we found is that the ASR models producing hypotheses faster than we translate. The effect was that the system was spending time translating that were obsolete and ultimately be replaced. In the animation, an example of a discarded event occurs when the like cheese without a period becomes obsolete. By discarding these obsolete events, we further improved latencies to 500 milliseconds at 90 percentile and 950 milliseconds at 95 percentile, a speed up that led to a smoother experience on the client and led to increases in the usage of the feature. Let's talk about user experience next. Specifically, we implemented 3 ways to input audio. The first method is tap and hold. In this method, the user holds down the source and target microphones to speak. Releasing will end the audio stream and therefore complete the sentence. The second method is a tap on the source or target microphones. This will start the audio stream and then rely on the speech recognition's end of speech model to stop recording and end the sentence. The third method is using the auto microphone, which I'll explain in the next slide. On the server side, using the auto mic, we process the audio stream through 3 models simultaneously: a speech-based language identification model, a source language model, and a target language model. After a second or so, the Lang ID model returns which language and a confidence level. Once the orchestration layer sees it, it picks the events generated by the higher confidence language and continues to use that model for future audio events. In this diagram, we see that the system has chosen the target language model based on the input audio. Overall, the experience is okay, but there remain many cases where it doesn't work. The endpointer isn't great, especially in noisy environments. Similarly, the Lang ID component is subject to error. As an alternative to improving the endpointer and the language identification model quality, we asked ourselves, what if we just kept the microphone on so that we didn't have to rely on those components? Turns out this is much easier said than done. We first collaborated with a separate research team within Google. These researchers and engineers were experts at sound understanding, and we're building a long-form audio input service for the deaf and hard of hearing. The research and development here identified 3 key problems to improve on. The first one is the codec. The second one is dealing with network timeouts, and the third is making sure that the ASR model is trained on long-form speech. And I'll talk about these things in a second. So for many years, we used what's called the adaptive multi-rate wideband codec for our audio input. It served us well, especially since we were focused on the user being close to the microphone. However, ambient noise and distance to the microphone were key factors in affecting word error rate for speech recognition. Investigation into codecs revealed that Ogg Opus provided superior quality when factoring in ambient noise and distance to the microphone. Dealing with the network timeout was incredibly tricky. The primary timeout came from the speech service itself, which would only allow for a maximum of 30 seconds for a session. But there were also secondary timeouts. Anything in between the client and server can cut off the connection. The key solution was to implement an audio buffer on the client and repeatedly reopen the speech sessions. These were then stitched together always to create this seemingly always-on connection. You can learn more about this through the Sound Understanding team's GitHub project, which I link here, called Live Transcribe Speech Engine. As to the speech recognition model itself, fundamentally, we needed a model that had to be trained on long-form speech data. For some time, YouTube had already built an automatic closed caption service. The key insight there was that we had to use their models that were trained on these long-form data from YouTube. And it performed much better than those that were trained for voice search applications. These in-domain ASR models perform quite well for the use case we were targeting. Once we had a better codec, solved the network timeout, and had a better model, we now have a better foundation that no longer requires an endpointer, and it no longer requires a lot of tapping on buttons. Okay, so now that we have long-form audio input in speech recognition in place, we started looking at the process of streaming translation more closely. In our first prototype, we translated on every update, as you can see here. Among the trade-offs of speed, stability, and quality, this implementation maximizes the trade-offs of speed and quality. To help better intuition around this prototype, we conducted user experience research, talked to professional interpreters, testing with what we have. Through the research, we tried many different use cases to see where the feature would perform the best. It turned out that a single speaker with limited background audio would work the best. In particular, lectures or a single person speaking at a dinner table in a quiet environment. With that focus on use cases, we began to test those scenarios with real people and quickly found that participants thought that what we had was disruptive due to rendering instability. So we decided that this was an important problem that we had to address. A naive fix would address this by optimizing stability and quality as seen in this example. Here, we translate after every sentence is complete. But as you can see, it takes quite some time to display translation. One of the things we learned in talking to professional interpreters is that listeners have a low tolerance for higher latency. Anything higher than 2 to 4 seconds is a very uncomfortable wait. With these learnings, we began work on how to stabilize the output of long-form simultaneous speech translation. Built on the work of several other research groups, we found a way to reuse off-the-shelf speech recognition and translation systems by using edit distance heuristics to stabilize the prefixes. We further improved that stabilization by making NMT, or the machine translation system, prefix aware. Through this, ultimately, we have found the right trade-offs between quality, voice-to-eye latency, and stability. The techniques of stabilization and metric evaluation were established by the paper Retranslation Strategies for Long-Form Simultaneous Spoken Language Translation. And here's what it looks like when we apply our research or our production system. As you can see here, the output text commits to a particular prefix early on and remains committed for the rest of the phrase. For many language pairs, we have found an excellent trade-off between quality, voice-to-eye latency, and stability. This slide compares the 3 approaches. At the top, you'll notice flickering. The word when and if are going back and forth. And that one is optimized for speed and quality. The middle optimizes for stability and quality. As you can see, it takes a long time for a sentence to show up. And at the bottom, a new approach finds a balance between all 3 of these concerns. Before moving on to text-to-speech and putting it all together, I want to point out another crucial technology that we had to implement for successful streaming translation, and that's unspoken punctuation. Examples here show how adding proper punctuation can change the overall meaning of the phrase. In the first one, let us see grandma, it's the meaning of wanting to see grandma, the Chinese translation. In the second, let us see grandma, it has the meaning of addressing the speaker's grandma and then the desire to verify some. The Chinese translation conveys this meaning similar. In our current implementation, we used a text-based recurrent neural network in post-processing. Turning this on allows us to increase quality. Some earlier analysis showed about an 8 blue point headroom in improving punctuation. Most recent evaluations capture about 3 blue points of quality improvement. So more research needs to happen to keep improving the quality here. Now on to text speech. Coming to the architecture stream speech translation. As audio is streaming in, we need to find the appropriate commit point to determine when to send text to TTS. This typically aligns with terminal punctuation or period. In animation, you can see partial results queue and waiting for that terminal punctuation before passing on to TTS. Let's consider the goals that we want to achieve for text-to-speech. The first is voice-to-ear latency. We want to make sure that the utterances from TTS are manner. As we discussed earlier, a listener is expecting to hear that TTS as soon as they hear the source speaker speaking. And the second goal here is, good prosody. Prosody means the rhythm and the sound produced is and how natural it sounds. And typically this is evaluated through humans to produce some kind of mean opinion score about it. And then a third sort of longer term, and I'll talk about this in a second, a longer term goal would be like, could we do this without a visual interface? With respect to voice-to-ear latency, there are a few challenges that increase the latency. The first one is the slow finality of speech recognition. It leads to higher sentence segmentation. So to solve this problem, we had to tune the system to finalize results in a way that we needed. In some cases, we weren't able to tune for certain languages, And so we haven't launched those languages yet. And the problem gets worse if we're using models, as I discussed earlier, it gets worse with models not trained for long-form data. Another aspect of latency is the TTS speed. In our implementation, we provided an explicit control in the user interface so the listener can adjust the speed dynamically. However, we have to be careful with speed, because as you adjust that speed higher, you sacrifice the prosody in how it sounds. Also, another aspect is that many TTS systems have input length limitations. So just like speech recognition, we have to sort of like make sure that the system isn't cutting off text in midstream in a sentence. Otherwise, that'll factor how it's uttered. Excuse me. When speech-to-speech translation is served without a UI, such as in the background, it requires a higher translation quality bar. This is because while looking at the user interface, the user has a way to compensate for errors that are made by the system. And another issue with a pure voice UI is sort of navigating. How do you get in and how do you get out? While I believe there's been a lot of progress in this space, I think we're still years away from a low-touch, pure sort of voice interface for speech-to-speech translation. So in putting it all together, I want to first talk about the process of evaluation and some of the lessons that we learned there. Then I'll show how the feature, what it looks like in the end-to-end product. As part of this effort, we wanted to see if we could set up a controlled environment and collect a quantitative measure of opinion from raters. Initially, we set up a process to have 3 bilingual raters watch a video in a source language and read the static target language text. Then we asked them to rate the adequacy, the fluency, and whether the text got the gist of the original meaning. The test set was constructed from 100 one-minute publicly available videos. We asked crowdsourcers to identify the videos and focus the domain on clean audio with one person speaking during that 1-minute video. In this experiment, we encountered a lot of problems. We found that the domain of test sets were misaligned across the languages. Some sets were easier for speech recognition than others. And we also suspected raters would click through YouTube's recommendation list, and that also introduced algorithmic bias in selecting videos. In addition to this, raters themselves were not very trustworthy. For example, understanding the source language introduced bias, and some rater pools were too small and were subject to biases like answering yes and agreeing to everything as being correct. So we improved upon the process in a couple of ways. First, we minimized video selection bias with better quality control. And the second thing that we did was we eliminated the bilingual bias by using sort of a monolingual template where we could just rely on raters that just spoke the target language. Overall, we ended up using this evaluation as a way to judge new languages we want to launch. Once a language is launched, we then focus on the automatic metrics as well as the feature being used through instrumenting the product. And here are the results. We launched support for 10 languages in March and recently launched streaming TTS support for Pixel Buds. In the animated GIF, you can see when TTS is emitted based on the highlighted segments. So to summarize, today I gave a high-level overview of the core components of speech translation. We learned that latency is important to users, but not at the expense of stability or TTS prosody. We needed a balance of all 3 to build a useful system. While we've made some initial progress on this, the road ahead is long and difficult. We're looking forward to further discussion and advancements in the field of speech-to-speech translation. So thank you everyone for your time. I'm looking forward to answer any questions that you might have.
Thank you, Jeff. So interesting, you know, just instant, we're used to now having just instant communication, and then as we diverse across languages, across cultures, it just gets more and more complicated, and the systems just need to keep up. So I have, you know, everyone please feel free to add questions in the chat. Some of you have A quick sort of compound question, I guess. I'll just compound it. How do you handle speech, any types of speech disruptions, whether it's the articulation of the speaker, and also, you know, code switching when somebody just uses, speaks with multiple languages, people, especially, you know, in English, core English countries, speak another native language, right? They would mix the languages, certain acronyms would be said in a different language, right? All of that. And also just syntax wise, right? When you switch from language to language, the phrase order, the sentence order changes in different languages. So as the simultaneous speech translation appears from speech to text and vice versa, right? How does that then seamlessly, because it happens like interpretation in real time, how does that, you know, right, offset, you know, or you know, really kind of think about the end of the sentence and digest everything and spit it out holistically. Right?
Yeah, so these are definitely interesting ongoing research topics and things that we don't perform very well right now, but these are definitely topics that we're super interested in. The first one you talked about is we call it disfluency. Sort of like as a person talks, they'll say something like, oh, I mean, and then they'll switch the word, and it's sort of like a whiteout process, but in more of a conversational, right? And a lot of times, and most of the times, professional interpreters, they pick up on that immediately, and then they make the adjustment and they sort of white it out in the target language. Our system doesn't do that yet. We're aware of that being an issue, and it's something that we're looking into. As far as code switching, that's also something that we're aware of and requires further research to get right, because there's a plenty of languages around the world where people are sort of mixing different words. And you know, when I actually lived in Taiwan for 10 years and learned Mandarin there, and while I was working there, you know, I was working in the semiconductor industry, and when I was working with people there, we would constantly sort of like flow back and forth between Mandarin and English, because English was used for like specific technical terms, while like the rest of the sentence structured around it was Mandarin. So it's a common problem, and it's something that we're thinking about.
Mm-hmm. So how are you thinking about the next languages? What prioritizes the next target peaks? And also when you run those tests, and it's very interesting, maybe you can talk a little bit more about the user research insights that you've gathered, but how, you know, is there a different, have you noticed varieties researching English speakers here domestically in the US versus target language?
Yeah, so I'll split that one up into two parts. So the first part is like, how do we qualify a language? And speech-to-speech translation is sort of like an end-to-end set of components that you put together. And that front component, the speech recognition, is like super critical. And so one of the first things right out of the gate that we look at is whether the word error rate of the transcription is low enough. And once it's reached a low enough error rate, then we start looking at the next component, is punctuation. Does it have a good way of adding commas and periods and question marks? Once that's in place, then we look at the machine translation and say, okay, for this language, is it decent enough quality? And so we have to sort of like break it out and look at these components from the beginning downstream from that. The second part is, yes, like specifically, I'll talk about raters again, in how we sent these things out for evaluation. There were different cultural biases and differences. Some cultures are very picky about how the translation comes out, and they bias very negatively in the rating. Some cultures are very lenient, and all of a sudden it's like everything is right, and we look at that and we're like, that can't be possible. So one example, there's a lot of examples that are complicated. So Japanese is complicated because it has a different grammar ordering, right? It's got verbs on the end. Arabic is another challenging one because it has so many dialects, right? And there's sort of like, we're very Egyptian biased in our Arabic, but a lot of television and a lot of informal videos are like sort of like more Syrian form of Arabic, for example. And so we definitely run into these kind of issues as well for dialects across languages.
Right, and actually, Catherine asked about dialects. It's you know, so you mentioned Japanese. So Japanese has 9 honorifics, right? So those are very, very different. You know, you cannot translate those into English because we only have 2, maybe 3 at least.
Yeah.
The Spanish between, you know, the Mexican, the Spanish for Mexico versus Spanish for Argentina versus Spain, Iberian Spanish are, you know, folks are very picky, very specific about their own dialect, their own vocabulary, their own slang, right? And when they get it spit out in the other, you know, if I'm in Spain and I'm getting it spit out in more Mexican Spanish, that doesn't feel that it's for me, right? And vice versa. So yeah, have you, when you've done user research in those, and of course Arabic, you know, there are so many different dialects that are really quite different in terms of the, even if the vocabulary sometimes, you know, oftentimes is shared, how you would use the vocabulary would be different. The context is different. The mindset is different, right?
Yeah.
Attitude. So how would you, you know, in the user research you guys have done, what, you know, have you seen those kind of?
Oh, absolutely. In fact, we don't have to do user research, right, because we have our apps, and there's like hundreds of millions of people that are submitting feedback all the time. And this is definitely a key piece of feedback that we see. One thing that we've explicitly have worked on is for some languages, we're able to resolve what's called gender ambiguity. Mm-hmm. So for example, there's some languages like Turkish are very ambiguous for gender pronouns. And then when you translate it into English, you know, we have to figure out how to convert it to either he or she, right? And it's a very complex problem, and we've applied solutions that are solutions we think can be used for both honorifics. So if we want to have some way to be more formal versus informal, and it is also a possible mechanism that we could use for regionalizing the translation based on like the dialect that they prefer. But this is all ongoing research. We don't have anything in a production system, and it's going to take some time because it's a very complicated issue. Yeah. And we recognize that. I mean, there's, you know, Taiwan has a very, very specific form of Mandarin has different vocabulary difference with mainland, and it's a problem that we're acutely aware of, but it's very hard work.
The switches between simplified traditional Chinese and all of that, yeah.
Even like vocabulary differences.
Okay, so. in the spoken languages. And also, so do you apply then, for example, I'm just curious because my native language is Hebrew, and the way we solve it, you know, is obviously languages that have issues, their users are more flexible because they know to expect issues, right? But you know, we kind of do the hyphen thing, right? Or not the hyphen, the backslash, right? And gender transmits also to singular plural, right?
Yeah.
And in terms of numerics in Eastern European languages, in Czech and other languages in Eastern Europe, you know, of course, the you know, many more pluralism, right? Conjugation of the verbs, right, and all of that. So are you able to kind of put some in the meantime until the models are better trained and until the system is smarter, to put all kinds of sort of generic rules to the piece?
Yeah, there's a lot of debate about that, and it still requires model updates to do that. It's not easy for us to do like you know, like a simple string replace, because there's a lot of conjugation rules and how it's interconnected between the sentence segments. So it's a very hard problem.
Right. All right. Well, good luck. You have a lot of work for the rest of your life. So that will be a big passion.
It's really fun.
Big mission, and yeah, very, very strong purpose. Thank you so much, Jeff. It was very interesting.
Yeah. I'll stay around for about 10 minutes in the chat. If anyone else has more questions, I'll just type answers in the chat.
Fantastic.